He's like, I don't feel like it's right now too. And so I'm just like sitting there. Yeah, she has a big old rat. She was like chow, 4th year. And she's just like sitting there. And she works for probably like 10 minutes. She's like, I'm gonna go take a break. I don't see her for a long time. I do an hour, I take my break, I do close to another hour. And then she like somehow comes out of nowhere. I was like, that's awesome. All right.
All right, good morning, everyone.
Good morning.
Good morning. Sorry. Activity for running long and talking way too much on the We're going to get started. And hopefully we'll be able to get through all of this so that we can do contrast tomorrow in our lab. So at this point, hopefully you have the understanding. I know that you've heard of MAR before. Hopefully you understand how to convert those acuities back to Snellen. We will go over them in lab when we have a little bit more time to work out some of those problems and that sort of thing. But for now, we're going to forge ahead. We'll talk about some more of the acuity charts that we use in low vision so that you're more prepared for lab tomorrow. So this chart right here that you can see the picture of is known as the fine bloom low vision acuity chart. And this test was developed many years ago, back in the 1900s, maybe early 1900s. And so this was one of the first low vision charts that were available, or that was available. And one of the interesting things about this that differed from a Snellen chart at the time was that it used numbers as opposed to letters. Now, whenever this test first came out, M acuities weren't a thing. We were still staunchly on imperial units, no metric units, I guess, I'm not sure. But everything was measured in foot letters. So historically, this chart was measured in foot letter format. Now, these days, new charts have M acuity available, so you can use either, just like with the lay numbers that we talked about yesterday. Now, one of the things that we have discussed at this point are Sloan letters, so letters that have a relatively equal difficulty of identification. You know, with the lay-in numbers, there's only about 4 numbers that are, well, there's only 4 numbers that are used in that chart, not only. There are 4 that are used in that chart, 5, 6, 8, and 9. And those you can even see on some of them, like the 5, the corner on the 5 has been clipped so that it more closely resembles a 6, so that hopefully they have relatively equal difficulty of identification. They're not Sloan letters, but they're close and equal difficulty. Now, if you look at the fine bloom chart here, what do you notice about the very first number that's shown right here?
The 7.
Very good. Excellent. Excellent observation. Are there any other numbers that really look like a 7?
No.
A 2.
So
Maybe. Yeah. A 1.
A 2 or a 1? Well, agree to disagree. No, I'm just kidding. Maybe you're right. I could understand that. What's that, Amber?
A 7 is a 7.
All right, there you go. Emma has spoken.
Yep.
So one of the things that I ran into with this chart is that this is not any kind of research. It's more of anecdotal evidence or anecdotal observations, I suppose, since that's a bit of an oxymoron. That this number is easily read by patients that then can't read any other subsequent numbers. And so in certain cases, I have observed this test overestimating a patient's visual acuity. And you might think overestimating, and you can see down here, this is a 700 foot letter. Yeah, overestimating just a little bit. And so their visual acuity is likely worse than is actually recorded, but they can identify that 7 because it looks like nothing else. This Berkeley rudimentary vision test is another one that we have in clinic. This was developed. Can anyone guess where this test was developed?
Berkeley.
Oh, very good. Man, you guys are on it today. So what this test was designed for was profoundly visually impaired individuals. And so in certain cases, depending upon how you use this test, you can quantify visual acuities up to 20 over 16,000. So remember, that's an optotype that would subtend 5 minutes of arc at 16,000 feet away, or roughly 3 miles. So in any case, these are really, I mean, folks who are profoundly visually impaired. Most of the time, what they're used for is not in like day-to-day low vision clinics, but things like just trying to identify if someone has any vision at all whatsoever. Research. Also, they've used them in like Special Olympics. Or Olympics competitions where you're pairing up visually impaired individuals against each other so that hopefully we can level the playing field in terms of vision. One of the things that sometimes I see recorded in charts, even after students have taken this course, is fingers acuity. or count fingers as the visual acuity. And sometimes students are astute enough to say count fingers at 3 feet or 4 feet, which is better. But what does that look like to you? An E, yeah, exactly right. So with our lay and numbers charts, even if you wanted to use the Feinbloom chart or even some of the other acuity charts that we have, we can quantify this much better in terms of being able to identify a specific optotype and therefore quantify a patient's visual acuity than if we just use count fingers. Again, at the very minimum, if you're going to say patient was count fingers, make sure that you specify the distance that your fingers were from their face. I don't recommend doing that. I do recommend laying numbers, even a Feinbloom chart over something like that. But again, if you don't have those, worst case scenario, make sure that you do record the distance that your fingers were from their face. So I threw some questions in here. In the interest of time, we can go over them in lab tomorrow when we have more time to chat. But think about these things. So we talked about Snellen acuity, how the denominator has to double if you have the working distance. Remember with M size, we don't have to do that. And then true, if you use legitimate foot letter size, we don't even have to do that. All we have to do is write the distance that the chart was at and the optotype size that the patient read, and that's it. So if you want to convert some of these M acuities to a Snellen or that 20/X format, there's a couple of ways that you can do that. One of the ways that we talk about, and I typically go over this in lab, again, I keep saying that, is something called the common multiplier. And I recognize that this is not a true mathematical word or vocabulary or whatever, but it's useful here because what we do is we take the numerator and we figure out what do we need to multiply it by to become 20. And whatever that number is, then we multiply the denominator by the same number. And so for instance, if you can see down here, this optotype size, which unfortunately I didn't label as 5/400 foot letter. This one in this case, whatever we would figure out 4 times 5 makes 20. And so then we multiply, I was looking for my pointer, 4 times 1400, and that would make 1600. So a 5/400 foot letter optotype would be equivalent to 20/1600. Down here, I did get my labels correct. And so you can see this 3/36.6 M. In that case, we would figure out whatever number it is, it's 6 something, multiply times 3 to give us 20, and we multiply that 36.6 times that same number to give us an acuity of 20/244. So for me, I can do most of these pretty quick if they're whole numbers, like this 5 or something. Whenever it gets a little hairy if you start throwing in numbers that aren't easily multiplied by a certain common multiplier to get 20, like 3 or 7, or I'm sure you can figure out some other numbers, but it gets a little bit more difficult. And so in those cases, what I typically do is cross multiply. And so cross multiplication, as you can see down here, and you could substitute that 3/36.6 M right over here. But in this case, we're going to use the 5/400. And so we write our acuity just like so, 20/X, and then we cross multiply. So it would be 20 times 400, which is 8,000. And then we divide that by 5. And then 5 times X would be 5X. And so now you've got things on either side of the equal sign. You divide out 5 to isolate X. That would be 8,000 divided by 5. Therefore, X is equivalent to 1600. I find that this is really, really useful whenever I'm doing Collenbrander acuities to convert that to Snellen acuities. And that would be angular. We'll talk about angular versus absolute size here in just a second. But in any case, I find it really helpful to cross multiply when dealing with the Collenbrander card. Because some of those acuities get a little bit weird. If the patient holds the chart at like 37 centimeters, and technically their acuity is like 0.37 over whatever optotype size that they read. I'm getting ahead of myself. We'll get to the Collenbrander here in just a second. So now, I guess. So for near acuities in our low vision clinic, please, please, please always use the Collenbrander. Never, ever, 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 ever use something like the reduced Snellen card, okay? For near acuities in low vision, Collenbrander card. There are near visual charts at the back of your lay and numbers chart, so that's also acceptable. But typically we use the Columbrander card for our near acuities. We do not, absolutely 100% do not use the reduced Snellen cards for reasons we'll talk about here in just a second. Now, on a lot of these cards, so you can see these near charts here, reduced Snellen, Runge, Rosenbaum, logarithmic 2000. They all have different acuities that are recorded on the side. If you've ever looked at those cards, they'll have Snellen, they'll have decimal, they'll have a couple other things. Sometimes they will have something called the Jaeger system. Have you all heard of this before? What's that?
I can't think of.
Say something humorous. What's going on? Fill me in.
People are talking about different kinds of Jaeger, Dr. Howe.
Oh, okay. Oh. Oh, well. All right, moving on. Thank you, Emma. I appreciate that. All right, so I did. So these are the different cards that you've probably seen used for near acuities. And so this one right here, second from the left, is that reduced Snellen card. And there's some issues associated with that we'll talk about here in just a second. But one of the things to note is on these cards, we have the Jaeger system. And this is typically abbreviated as J and then a number. So like J1, J2, so on and so forth. Now, the thing that's weird about the Jaeger system is that the print size is actually variable. So there's not really a standardized 5 minutes of arc at such and such distance or anything like that. It's not even like your reduced Snellen cards where the size of the letter, the absolute size of the letter at 40 centimeters will subtend the same as a 20/20 optotype on your chart. So there are some problems associated with this. For instance, if you look at a J2 optotype and you compare it to a J4 optotype, you would think, just based on the doubling of the number, that the optotype would be doubled in size. But it's not. And there are variabilities even between charts. So I guess the answer is, why would anyone ever use Jaeger acuities? Or the question is that, and my answer is, I don't know. Now, there are instances for certain government eye exams. Back in the day over in Stillwell, when we had to do C&E exams on their employees, they would ask for Jaeger near acuities. I have seen it occasionally in military applications, but talking to some of the other, like Dr. Struble and some of the other folks that have come back, apparently they have phased this out. So it may not be as much of an issue anymore, and I may not have to talk about how bad it is, hopefully in the future. The reduced Snellen card, again, poor image quality. I need to find some better, higher resolution images, I guess. It didn't used to matter whenever our projector was horrible in 104, but now it does. So one of the things about this card that you've probably seen is that the card must be held at 40 centimeters or 16 inches. If you hold it at some other distance, then effectively you're changing the acuity, whether you realize it or not. And so it's held at 40 centimeters for a very specific reason, and I think that's on the next slide or the slide after. However, one of the things that can be ambiguous about this chart is perhaps you're pretty savvy and you realize, hey, my patient held the chart at 20 centimeters or held the chart at 25 centimeters or something like that. Well, I'm going to record that in my notes. So you might try to say something like 20/40 at 20 centimeters. Now, to you, that makes perfect sense. That means that the patient held the chart at 20 centimeters and they read the 20/40 line. But somebody that comes after you that reads that could think that, of course, that's one of the options. Or they might think that the patient read the 20/20 optotype at 20 centimeters. And because that was half the distance of the calibrated chart distance, then you just basically doubled the optotype size that you converted it already for them. And so effectively, that would be an example of an incorrect visual acuity, and therefore it would be difficult for them to repeat that and find that. So again, the results can be ambiguous unless you spend a lot of time detailing exactly what you mean by 20/40 at 20 centimeters. One of the things that, I don't know if you've heard this or not, so if you have, please let me know and I'll skip ahead. One of the things about this chart is, have you ever thought, well, the patient is 20/20 at near, but they're 20/20 at distance. How does that work? Because we've already talked about what 20/20 means, right? This optotype is a specific size so that it subtends 5 minutes of arc at 20 feet. Well, you're holding your card at 40 centimeters. So obviously we've already got one thing against us. Now the letters have been calibrated, but they've been calibrated such to a size where since you're holding the chart at about 15 times closer than a 20-foot distance, they're about 15 times smaller. And so the angular subtense, if you look specifically at the angle that the letter subtends from the chart, and then hold the 20/20 line up right next to it at 40 centimeters, they are about the same size. So they calibrate these cards based on the letter height, not necessarily that same rule that we talked about where it's a 20-foot optotype at 5 minutes of arc at 20 feet. So let's see, a 2050 optotype, and we'll talk about this in just a second. I suppose I could kind of let the cat out of the bag. This is equivalent to a 1M optotype size. So a 2050 optotype on your near acuity card is 1.454 millimeters. And then from there, we can determine the absolute letter size of other optotype sizes on this card, and we can compare it back to M acuities. The takeaway point with this is, again, don't use the reduced Snellen card for your near acuities, especially in low vision. If you're going to do it in primary care, then you really need to have it at 40 centimeters, and don't let the patient bring it closer, even if they're wearing a +3 ad or something like that. If they are doing something, then you're just going to have to get a different chart. It's sort of the long and short of it. There is another system here called Printer's Points. So make sure you put a star on this one. Because I will ask you questions about it. You do need to be able to convert your M acuities to something called Printer's Points. And this is an approximate computer font size. Now, of course, there are variations between, something that's more of a script size font versus something that's more like Times New Roman or Arial or something like that. However, if it's a general print, then most of the time the sizes are pretty similar. And so what we can do is we can take the M size or the M acuity, the optotype size that they read, and multiply it by 8. And therefore we can tell teachers if they're trying to print up materials for a student, and that's, I guess I got ahead of myself. This is typically who I use this for. So over at the School for the Blind, teachers like to print stuff off for their students. And so I explain to them, if you're going to print something off, then you need to print it in size X font, whatever it is based on the patient's M acuities. So in this case, the patient was able to read 2M, and so 2 times 8 is 16. And so I would recommend printing off material in 16-point font at a minimum for the patient to read it. Now, a lot of those kids will alter their reading distance, and some of them will read like with a card 10 centimeters in front of their face. And of course, this is, it makes our acuities, by bringing it that close and looking at that large of a letter, our acuities are really, really poor, but they can still see it. And so acuity isn't quite so important in that context if they can still read what they need to read. So as I mentioned before, use the M system whenever we're in low vision clinic. The argument could be made that this is a better way to do it, especially if you're going to try to measure acuities on a patient at some distance other than 40 centimeters. But as I realize, it's kind of futile to keep saying this over and over. I will say make sure that you use the Colin Brander card in low vision. And then just maybe at least remember that if you move that near point card to some distance other than 40 centimeters, you are altering the visual acuities. And therefore that Snellen acuity is no longer valid on the side of that card. This is talking about looking at the absolute size of some of the letters of the M optotypes. And remember, with the M acuities, then there is no reduced M. There is nothing like that. Again, all you do is have the patient read the optotypes that they can, and you record the distance the card was at and the optotype size that they read. Now, depending upon the patient, it can work out to where if the chart was at 4 meters and now they're holding their card at 40 centimeters, then you can see that direct, tenth of a change in their acuity. For instance, if a patient was able to read 16M at 4 meters, and now the chart is at 40 centimeters or 0.4 meters, then we would expect them to read about 1.6M in that context. So just move that decimal place 1 place to the right, just like we did for the distance, and that's what we would expect to see in terms of acuity. As I mentioned before, the absolute size of the 1M letter is equivalent to that 2050 reduced Snellen, or 1.45 millimeters. 1.454 millimeters. So we can use this to convert from reduced Snellen to an approximate M size. by either absolute size or by, since we know 2050 is equivalent to 1 M, we can determine, and we can go from M to reduce Snellen acuities as well. So this is the Colin-Brander chart, of which I have long spoken about at this point. And you can see that there are 2 columns of letters. Now there are similarities here to that ETDRS chart that we've already looked at. But instead of it being a nice sort of triangle, like an isosceles triangle, we kind of almost have kind of a right triangle sort of thing going on, where the letters kind of taper to this edge, as you can clearly see. On the other side of the card, what do you notice about these letters over here?
Less contrast.
Reduced contrast, exactly right. And so in this case, the letters on the right have a 10% contrast, depending upon the style that you use, Weber or Michelson. But they have approximately a 10% difference or 10% contrast relative to the 100% contrast on the left side of the card. So having this contrast available to us with the Colin-Brander chart is a bit of a two-edged sword, because on the one hand, it encourages clinicians to think about maybe testing contrast and checking it and seeing if there's any reduction or any potential loss of contrast. On the other, as we're going to find out here in just a little while, this particular chart does not quantify how much contrast the patient has. It will tell you if they have a deficiency, absolutely, but it won't tell you what their deficiency is, and therefore it can be somewhat difficult to track from exam to exam. So in low vision, we do have a chart that will quantify. There's a specific number of letters that we'll talk about. It's called the Mars chart. And we're going to look at that because with that one, we can figure out exactly what that patient's contrast is at that specific time. And we can repeat it from exam to exam, just making sure or being able to realize if their contrast is changing. So over here on the side, on either side here and over here, since these letter sizes are the same, again, you can see M over here on the left, and then these few different acuity sizes on the right. So 20/20, Snellen, decimal, that sort of thing. Now, remember that with the Snellen acuities, you have to read the chart and find out what the distance is calibrated or what the chart is calibrated for. And those Snellen acuities are only valid for that specific distance, just like the reduced Snellen card that we just talked about. So if you're going to use the Snellen acuities, the chart in this case has to be held at 40 centimeters. Now, the ones down in our clinic, we've got maybe 2 different ones. One is 40 centimeters or 2 different styles. One style is 40 centimeters and the other is 100 centimeters. So just make sure, I don't recommend recording in Snellen, but if you were, then the chart has to be held at 40 centimeters for that to be accurate. Or you'd have to convert. And if you're going to convert, you may as well just use M. Now, what I mentioned before about this being a two-edged sword, again, it encourages clinicians to think about doing the contrast. And the way in which we do that, we'll talk about here in a second, is looking at the number of lines lost. And so if the patient loses approximately 3 lines of acuity, then that indicates that they may have contrast impairment. So in order to use this card, what we like to do is have the patient hold the card at their habitual distance. Now, as you know, sometimes patients aren't great at this. You would think that they would be able to kind of move that chart in until they find it in focus. But I've seen people using 33 centimeters working distance for a 250 ad. I've had patients go the other way and try to use 40 centimeters for a 3 diopter ad. So patients are not always the best at determining the correct working distance for whatever glasses that they're wearing. However, at least at the start, what we typically try to do is let them select their habitual working distance. And we have tape measures in low vision, and we get out the tape measure and we record and we see what that distance is, and we write that down. So then after we write it down, we encourage the patient to not move the card. I tell them something along the lines of almost exactly this. You may be tempted to bring the chart closer to read further down the chart, but for this test, keep it at this distance. The other thing is that you don't want to change this distance between eyes. So if you're testing the right eye first and they hold the card at 38 centimeters, you move it over to the left eye and they try to move it, you can't allow them to move it. Otherwise, it makes it difficult to compare, at least just straight across without converting. And so we typically make them hold it back at that 38 centimeter working distance, as in this example. So we don't want to do this. 28 centimeter distance for the right eye, 36 centimeter distance for the left eye. We don't want to do that. We want to have it at the same distance for each eye. Of course, just like every other chart, we want to push the patient down the chart, encourage guessing just to get the maximum acuity, determine hopefully their maximum threshold of acuity so we know exactly where they're at. Just like with the ETDRS, if you so choose, you can count the letters and then you can quantify their acuity that way as well. We don't have to do plus minus as much like we do Snellen or just kind of hide our head in the sand about letters that a patient didn't see along their ways down the chart. The other consideration that some of these have, in this case, this column brander on the back of the card has continuous text. So you can see here that there are short sentences that the patient can read. There's a few different other ones. We'll talk about the MN read test in a future lecture, but this is basically the same thing where the patient reads short passages of text, and in that way we can determine how their reading performance or how good their reading performance is. There's also another one called the Lighthouse that we don't have here in this clinic, but just in case you're interested in different types of reading acuity tests. Again, note the Jaeger ranges here. So the J numbers, as you can see, again, this varies 14 to 18, 7 to 18, 6 to 14. And so there are variabilities in that J number there, as you can see on the chart here. Now, have we talked, I probably mentioned this before, single letter acuities tend to do what to reading ability? They tend to overestimate or underestimate a patient's reading abilities. Overestimate, exactly right. I'm sorry for my poor phrasing of that question. When we look at single letters, we tend to have better acuities than we do whenever we're reading. And that's because of reasons we talked about last year. We don't read individual letters. We read, in some cases, we don't even read all the words in a sentence. We chunk large groups of words together. So because of that, saying a patient is 20/20 reduced Snellen and going on with your day may not be the whole picture of a patient's reading ability. That's why in low vision, especially, we do these continuous text style visual acuity tests. So if you've got a reduced Snellen card, kind of wrapping this little bit up here, you've got a reduced Snellen card and you want to convert to M, or you want to convert from M to reduced Snellen, there's 2+ different ways that you can do that. So over here on the left, you can see you can convert to absolute size, or you can convert on the other way is angular size. So over here on the left, you can see absolute size has 2 different ways, the absolute size here, and then the reduced Snellen based on absolute size. So if we know that a 1M optotype is 1.454 millimeters tall, and the patient reads a 1.6 millimeter or 1.6M optotype, then all we have to do is multiply 1.6 times that height of that letter to know the absolute height of a 1.6M sized optotype. I don't know why you would do this. I've never had to do it in clinic. Just in case you ever come across this, hopefully it'll be useful for you. If it's trivia night or something like that, you can do it. What is more useful that I found is the reduced Snellen equivalent down here. And that's where we know that a 1M optotype is equivalent to a 20/50 reduced Snellen optotype. And so if we still have a 1.6M optotype size the patient read, we can convert it just by multiplying it times 50 to get a 20/80 reduced Snellen optotype. So it's a good way to kind of compare between charts. Patient read a 1.6M optotype on this chart. We would expect them to be able to see a 20/80 optotype size on the reduced Snellen chart. Over on angular size, remember that with the M acuities, since it is based on angular, you can convert directly to the angular Snellen. And so I recommend cross-multiplying in this case. And as you can see here, this is one of those weird ones. Maybe you can do them in your head, but I can't. And so I would put this in a cross-multiplication where 0.3 would be on top, 1.6 on bottom, equal sign, 20 on top, X on bottom, and then I would multiply. And so it would be 20 times 1.6 and then divided by 0.3 in order to get that acuity of 107. And that would again be the angular Snellen equivalent, not the absolute size. So this is just an example. What this is basically talking about is, well, let me make sure I'm at the right spot. Okay, So this is an example of what happens if you move that reduced Snellen near acuity chart closer than some distance than 40 centimeters. And so you can imagine the scenario, you're in the clinic, you measure a patient's acuity, and at distance is 20/25, you put the +3 add in front of the patient and have them hold the card at 33 centimeters. So in that regard, you did well. You paired up the correct lens power with the correct working distance. And that's very important. It's very important. But because we've now moved this chart closer than 40 centimeters, basically what's going to happen is we're going to overestimate their acuity. And so likely in this scenario, you would end up with an acuity somewhere around 20/20 because the chart is closer than 40 centimeters. So you can see here and kind of go through this, but effectively what we would find if we actually looked at the angular Snellen equivalent of this M acuity of 0.33 over 0.4 M, which takes into account the distance and the optotype size that the patient read, would be that their visual acuity, whenever we're looking at an angular acuity as opposed to absolute size, the visual acuity of the near card or the patient's near vision is 20/24 in this case, which is equivalent to their distance acuity, which is what we want and what we expect. If a patient is properly corrected for near, the ability of their retina to resolve those letters should be the same at distance and at near. And so if they can read 20/20 or let's say 4M at distance, then we would expect them to be able to read 0.4 at distance with that closer working distance. We would expect them to see basically the same or have the same angular acuities. So looking at revolution, one thing to be sure of is that they've sort of resolved this at this point, but at any time they could kind of flip back and forth. They have had these switched from your primary care tabs before where it said aided over here and unaided over here, or vice versa. So make sure that you're recording acuities under the correct spot. And what do you notice about the near acuities? What's wrong about that recording nomenclature there? Centimeters. So you're not wrong. Yes, you are correct. Centimeters. You just do a straight conversion. For intents and purposes, that's okay in terms of like being able to record it because you are recording the distance. But you're right, we do typically record it in meters. And so if I were writing down these acuities, I would still put, if it were 40 centimeters, I would put 0.4 over whatever optotype size that they read. And if you were listening, I kind of gave away the answer. So how do we order our acuities in M? Should be the distance and then optotype size, right? For whatever reason, revolution has made it to where optotype size comes first and then distance, and they're sticking to their guns on this one. I don't know why. We've asked them to switch it and they said no. Thanks for the input. Your input is incredibly valued. We'll talk about it at our next Teams meeting, but ultimately the answer is no. Thank you for your response. Let's see. So recall yesterday, if you want to be a pro in low vision, then you need to think about the chart that you're using and the patient's entering visual acuities. So if the patient can see better than 2200, you can use the chart at 4 meters. If the patient is 2400 or so, or maybe just slightly better, but not quite 2200, you have to use 2 meters. And you have to basically base the incoming acuities or use the incoming acuities in order to determine where you want your chart. And there's nothing wrong with using a shorter working distance. There's nothing wrong with this at all because most of the folks that we're working with are already presbyopic. So it's not like we're causing them to accommodate or anything like that. And because of something that we'll talk about called just noticeable difference, where a patient, we have to increase the size of our lenses that we show them, but it also doesn't, it won't make a huge difference if the chart is closer. It doesn't make a huge difference for patients' visual acuity. So we want to make sure that they get further down in the chart where they can get some crowding phenomenon. They don't just read the top line and we roll with that. We have to make sure that they read a couple letters or, down into that second line. So ETDRS is the preferred chart for distance acuities. Colin Brander is the preferred chart for near acuity. So this was designed to test your knowledge. We'll go through this pretty quick. Let's say that the chart was held at 20 centimeters and the patient read the 2.5 M line. How would you record this acuity?
0.2 over 2.5.
Very good. Exactly right. So if you converted this to Snellen, remember common multiplier, you can do the cross multiplication, or if you kind of realize like, hey, this 20 is a 0.2, so all we got to do is just move the decimal place two places to the right, 2 places to the right over here, and now we have our Snellen acuity. So that's sort of a third way that you can convert these acuities to Snellen. Now, does it matter that we held this chart at 20 centimeters instead of 40 centimeters for the acuities that we just spec'd?
No.
No. Do we need to modify anything on our end, on our M acuities, to account for this shorter working distance?
No.
No, because we have already done that, right? We recorded the distance that the chart was held at. We recorded the optotype size that the patient read. So we're done. We don't do anything else. We don't do any weird conversions. If for some weird reason you decided I want to record these in Snellen, which I do not advise, then you would have to double your acuity. So in this case, let's see, 2.5 M. It's equivalent to 20 over 125 over here. If the chart is held at 20 or 40 centimeters, but since it was held at 20, we would have to double the size to 20 over 250, which is where we were before. So you can test yourself. I'm going to skip through this in the interest of time, but these are really good because on the next slide, which I'll go through as well, it's got the answers. So you can ask yourself the answer, or you can quiz yourself here and see if you come up with the same acuity that I did. One thing I didn't put here, but as I was reviewing it this morning, I did put no other letters were read. So once they get to this line and they only get 2, that's where the test stops. So the patient read 18 letters correct. And you can see all my math as we went through there. So this is another one where I didn't put the chart per se, but I just gave you another option. The rub here is that the chart is held at 2 meters. Now for us, if we're doing M acuities, it doesn't matter again, because all we would have to do is consolidate the number of letters that they read and then record the optotype size and the distance. So 2 meters over whatever optotype size the patient was able to get to, and then we could be done. But if you wanted to do the exact logarithmic acuity, there's 2 ways that you can do this. You can account for the test distance at the end. And so you can do it the exact same way we already have, where you multiply the total numbers times 0.02, and then subtract that from 1, and so on and so forth. Once you get down, you've got the MAR, you multiply it by 20 to get the Snellen denominator. So at this point now, you've done all this math as if the chart was at 4 meters. But since the chart is at 2 meters, we have to double that denominator. And that's what you would do here. So this would be basically rectifying that shorter working distance at the very end of your log-MAR equation here. The other way to do it is to account for the test distance at the start. So if you go through the math and you look at a 2200 optotype, and then you get the MAR from that, and then you take the log of that MAR, then a 2200 optotype moved up to 2 meters is now equivalent to 2400. And so 400 divided by 20 gives you a MAR of 20, and then you just basically punch in log on your calculator and it'll spit you out a 1.3. Now, this is our base. So instead of a 1.0 like we talked about before, we have to use 1.3. And then we would subtract the number of optotypes that the patient read beyond the top line, and that would give us that same number. So 0.36. So 18 times 0.202 would give you this 0.36. But then you take it from the 1.3 instead of 1.0. So in this way, you're accounting for the differing test distances at the beginning of the equation rather than at the end. It's really up to you. You come out with the same numbers. This would probably be more handy if you were having to convert from like 4 meter acuities to 3 meter acuities or something like that. If you're just gonna move it up 2 meters, then you can just basically double it and be done, in my opinion. Yes.
Would you ask us to do that level of conversion on like a test question or something?
Yes. Yes. Yeah. So that's definitely good test fodder. In a clinic, no.
Okay.
But the thing is that I've had students tell me that there are some of these equations, and at least if you get comfortable with logmar, if you see it on boards or if you see it while you're doing all the research papers and everything, then you're a little bit more comfortable. You understand what it means. So it's good to kind of have this knowledge. In practicality or in clinic, it's probably not used very much, at least not here. This is just something else. I'll let you kind of read through this, but basically the same. Talking about the same thing, rectifying the shorter test distance at the beginning of the equation instead of at the end. All right, so let's get to the last part here, talking about contrast, because for tomorrow's lab, and since I'm talking about it now, you don't have to bring any equipment. You just need to show up. I printed off the same number of labs as I had last week. So if you did it on paper, I'll have one for you. If you did it on your computer, then it is available on Blackboard, and I'll expect you to download that, or I can scramble back upstairs and print another copy. But in any case, tomorrow's lab is going to be over visual acuity, what we talked about yesterday and today, and contrast, which we're about to talk about here. So we'll be able to do all those in lab tomorrow. So I've already regaled you with tales on how contrast is great. Testing it is wonderful. We don't do it enough in regular clinic, that sort of thing. And all those things are true. We don't test it enough in clinic. You've probably had a patient, and if you haven't yet, you will likely have one in the future that says like, well, I'm having trouble reading the newspaper or some book or something like that, since newspapers are not as much of a thing anymore. And you'll check their acuity with perhaps a reduced Snellen car, being careful to hold it at 40 centimeters. And maybe they're still able to see 20/20. And you're sitting there kind of scratching your head like, this patient's complaining about not being able to read, maybe in a sort of reduced contrast situation. But here in my clinic, when I've got these super bright lights and 100% contrast chart, they're doing fine with single letters. Now, we've already talked about how single letter acuity tends to overestimate reading ability. But one other aspect that you need to consider is contrast. In our clinics, of course, our charts are 100% contrast. We got super bright lights, so we can increase the contrast as well. But in reality, contrast isn't 100%. And whenever patients are reading things, it's typically also not 100%. So it is another important thing for us to assess. Now, if you think back to Vision Science 2, remember that there are two ways that we can measure contrast, the Michelson method and the Weber method. Is this going to come up in clinic? No, but remember these things. And really what I kind of want you to pay attention to is the difference in these measured amounts of contrast between whenever you have a bright or a high contrast and a low contrast. So if you have high contrast, both the Michelson and the Weber equations are going to give you roughly the same amount of contrast. I realize that there's a difference, but they're pretty close. Whenever you have lower contrast, then you can see that the Michelson equation is going to give you much lower contrast relative to the Weber equation. Does this matter? No, not really. But I am making sure that you understand that there are some differences in the equation so that you are aware of just the differences in the math in order to come up with these contrast estimates. So remember back to Vision Science 2, where you talked about the difference between sensitivity and threshold. So remember, if sensitivity is high, then threshold is low. Correct. And if threshold is high, then sensitivity is low. Exactly. So there's an inverse relationship between those two terms. And so what we would like to see is all of our patients have very, very low thresholds to contrast, very easy to see the very faint letters and that sort of thing on our chart, and therefore very high contrast sensitivity. Unfortunately, that's often not the case. And so when we were looking at our chart, what we're trying to see is how low can they go? It's kind of like a limbo, I guess. How low on the chart can they go? How many letters can they get correct? On contrast, more is better, just like everything, right? One thing to note is that contrast sensitivity is a unitless value. So this is one thing where you don't have to try to think of a number or think of a unit rather to go along with your answer. It's just whatever it is. In this case, most of the time, we use log of contrast sensitivity. And so we just record that value, record those numbers in the appropriate box in Revolution, but it is unitless. So I've talked about this a little bit. Contrast is important, blah, 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 etc. One thing to note is that if you have a normally sighted individual and you start varying contrast, then it doesn't seem to affect their reading speed until contrast gets below about 10%. So even in a normally sighted patient, contrast is important. And if the contrast gets too low, then it makes their reading speed go down. When a patient loses contrast, so our low vision patients that come in and they lose contrast, what they typically say is, sometimes I find with a really, really large print or really, really small print, those are more difficult to see. And that all has to do with that, that curve, that contrast sensitivity function curve that you all know and love from Vision Science 2 that relates spatial frequencies to contrast. And so whenever the contrast or whenever the letters are very large or very small, remember that's at two ends of that arc, right? Way down here and way up here. And so when you're right in that middle or right at either end of that zone, then contrast or loss of contrast is going to affect these patients a lot. Right in the middle, that CSF curve, what is it, like 4 cycles per degree, something like that? Yeah, see? That point, if it's kind of right in the middle of our spatial frequencies, then that's where we have our maximum contrast sensitivity. These two graphs are just showing you that lower contrast equals poor reading performance, and I've already said that. I've already mentioned as well some of these things, you know, life, everything that we see in life is not 100% contrast, and there's just some examples here. I saw this one on a Reddit or a subreddit, and it was like mildly infuriating, I think was the subreddit. And it was like pouring black coffee into a black cup or pouring coffee into a black cup, how, you know, contrast issues. It's like, so, you know, there are some instances of even normally sighted patients dealing with some of these low contrast problems as well. This is kind of a cool, what are those called? Like a, help me out. It's one of those things where over here on the right, you know, this brown looks a little bit darker. This one looks a little bit brighter. But if you compare the two things together, they're exactly the same. So kind of a little bit of a trick there. And that's based on perceived contrast. So we'll talk about the Berkeley test for contrast. This one utilizes filters instead of a chart in order to measure contrast acuity. And so you put a 100% chart, 100% contrast chart in front of a patient, and then put 4% visible light transmission glasses on that patient. And it effectively reduces the contrast then, and you see how well they perform. And if they lose 10 letters or more on the ETDRS chart, then you have abnormal contrast. And so you have some problem with the contrast. But this is an example, again, like the Collenbrander, of qualifying contrast loss, not giving us a specific amount of contrast that the patient has left. So moving into quantifying contrast, we first have the Pelley-Robson chart. Now these are kind of cool. They're like almost poster board size contrast charts, and they mount on the wall. The patient has to stand or maybe sit in certain instances, if you've got it set up that way, 1 meter away from this chart. And then for each triplet, so each 3 letters here, that's like VRS, for instance, those are all the same contrast. And so those would all be 100% contrast. And then as we move over here, then we have 0.15 log units less of contrast, and then so on and so forth as we work our way down the chart. Now this is a fine chart. There's nothing wrong with the Pelley-Robson. The difficulty is that since it has to be typically mounted on the wall, uniform luminance can be an issue, mobility can be an issue if you don't have some chair or something sitting in front of the patient. So there are some issues with it, but it's a fine chart and there's nothing wrong with using it. The chart that we use in clinic is the Mars chart because it takes the Pelley-Robson and it changes it just a little bit to where we can have a varying working distance. Working distance is a little bit, it doesn't have to be quite as exact. It can be held anywhere between 40 and 60 centimeters without really any loss of our contrast or any major changes in contrast. This one has letters that decrease in contrast by 0.04 log units for every single letter. So the only letter on this chart that is 100% contrast is the very top left one. So in this case of this chart here, it's the H. This one is 0.04 less, this one is 0.04 less than that, and so on and so forth. Let's see. The Sloan letters are used on this chart. So remember, letters that have relatively equal difficulty of identification. And then what we try to do, or what we do with this test, is we have the patient read the chart, and we push them as far down the chart as we possibly can, and we count the number of letters that they get right on the way down. We stop the test whenever they miss 2 letters in a row. Miss 2 letters in a row, test is done. You add up the number that they got right, you multiply it by 0.04, and that will give you a specific log contrast sensitivity for that patient. which then you can use on each subsequent visit to track and see if it's changing. Depending upon their contrast, that number that you found, we have these ranges here that indicate how much contrast or what kind of contrast sensitivity the patient has. Is it normal, moderate loss, severe loss, so on and so forth. And this is what I was talking about here. The multiply each one by 0.04. Stop whenever you get to 2 letters missed. So in this example here, you can see we would stop right here. Okay. All right. So tomorrow in lab, let me hold on one second. Hold on one second. Let me make sure that there's nothing else that we need to know for lab. And after that, you can start packing everything up. Make sure that you know those ranges. Well, we can catch up on some of this next Monday because there are 2 other contrast sensitivity charts that we use in clinic. But make sure that you understand how to do the Mars and how to do the Colin Brander contrast side of that chart. Okay. Are there any questions? All right. Have a good day. Yeah.
It was so funny. And when. Yeah.